All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and get started. First off, good afternoon. I'm Jason Thomas, Portfolio Coordinator at America Makes, and I'll be your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of today's presentation, there will be an opportunity for a question and answer session. If during the presentation you do have a question, please submit it in the Q&A space on your WebEx screen, and I'll ask it during the Q&A session. I will do my best to get all of your questions answered. Today's webinar is on the top 3 reasons to leverage simulation in additive manufacturing. Now, without further ado, it is my pleasure to introduce Christopher Robinson. Christopher is a Senior Product Manager with Ansys. Chris, I will now turn it over to you and your team.
Excellent. Thanks, Jason. I am always excited to get opportunities to talk about simulation for additive manufacturing. Before we even jump into talking about an agenda and other things that we're talking about, I really want to just talk about why I'm here today. Some of you have seen me present previously. You'll see similar things like this, but I absolutely believe that additive manufacturing has the ability to improve the quality of life around the globe in this generation and in future generations. Just a couple of examples of what I'm talking about there. We've got specific medical applications. We look at sustainability, carbon capture, and obviously, there's a lot of push right now, lots of valid push for fewer emissions, which is critical to becoming carbon neutral. Many companies have that target of 2050 becoming totally carbon neutral. Additive manufacturing is definitely a way to achieve that, as well as so many other applications that are life improving. At Ansys, our vision here with additive is to be able to enable anybody utilizing additive manufacturing to access the insights where and how they need them to enable the efficient production of life improving products across AM processes and industries. And so, when we look at that, this is really what is motivating me and why I'm here today. So now jumping into kind of an agenda, what are we going to do today? So yes, going to be, I want people to buy Ansys software, yes. But that's not why about 7 years ago, I left the aerospace AM R&D industry and moved into simulation. The reason I moved into simulation is because we needed simulation tools in order to make the additive manufacturing industry grow. I knew I could help bring them to fruition. And now that there are such amazing tools out there and available, I really want everybody to know how they can benefit from the tools. So today, we're going to talk about 3 specific reasons and 3 key reasons for leveraging simulation for additive manufacturing, which is reducing cost, increasing reliability, and accelerating the qualification of machines and or applications. So one of the things that we'll do as we go through this today is answering some basic questions out there. So, things that are fairly basic and relative to additive. What are some applications where additive is right? Why should we consider simulation for additive instead of just build, test, and trial? How can simulation technology actually reduce your costs for additive? We'll talk about what, answer the question of what is some of the terminology relative to additive simulation, and then talk a little bit about what some of the tools we should use are. So diving into it, question number 1, what are some applications where additive is the right technology for for producing good components. And now I know a lot of you have probably seen this before. It's out there. It's an amazing example of a heat exchanger. So these the 6 companies across the top, Topology, Ansys, EOS, NSI, Synopsys, and Stress Engineering Services, joined together to be able to create a heat exchanger example here. And so taking on this example, or this challenge of being able to design an improved heat exchanger, was a really awesome demonstration of what additive can bring to the industry. So the results of this, I'm not going to go into a ton of details on it today. We've presented on this quite a bit. There are a lot of, there's a whole Synopsys webinar series that you can go and look up if you're interested in that. But the results of this challenge, as you look at this component on the right, the gray geometry is the original design. The light blue geometry is the result of this redesigned heat exchanger, which was a consolidation of 40 parts down to one single printed part. The heat transfer was doubled in only 20% of the volume. There was over 9x reduction in the pressure drop as you go through this heat exchanger. There was a successful print on the very first attempt, full NDE inspection with 0 defects, and then at the completion with the as printed, the as built part, the ability to run full heat transfer simulations. So that's just one example of a great application for additive manufacturing, and shows some of the value that additive manufacturing can bring. Just a couple more ideas kind of around the promises that additive can bring. You've got geometries that are impossible to build with traditional manufacturing technologies. You can create functional materials and geometries as well as graded materials. You can look at part consolidation, one of the key things we were just looking at, as well as when we look at sustainability, being able to really drive optimized designs. And additive manufacturing provides a really viable method for being able to produce these optimized designs that lead to further sustainability of products. So now we jump into that question of why should we consider simulation for additive? Many of you may have seen this, the Simon Sinek golden circle. As we look at this, kind of look at why, how, and what. And really the reason that simulation for additive is beneficial is because of those things like cost, repeatability, and part qualification. And the way that we get there is through simulating the metal additive manufacturing process. Some of the key things, there are many things that we do simulate. Some of the key ones are hardware crash. You know, if you're using laser powder bed fusion, you have a recoater blade that could easily hit into your part if you start to get Z direction deformation. Distortion compensation, we'll talk about some of this a little bit later on in more detail in the presentation, but oftentimes your parts don't come out exactly as you had designed them. And so we can predict what's going to happen and compensate for that distortion before you ever start to melt any powder, or before you start to bind material together if you're doing binder jet. Also, material failure. So whether that's in the supports, whether it's a connection between supports and base plate, whether it's when the part itself generates enough residual stress that it'll rip it apart. And this happens across different manufacturing processes, some of which that we focus on are laser powder bed fusion, DED, and binder jet. So as we look at that, just another quick look into some of those challenges that you have with additive manufacturing. Yes, those promises are amazing, but sometimes the challenges end up holding us back. And so as we look at some of those challenges that can be addressed through simulation, we have things like your process parameters, particularly if you're looking at the laser powder bed fusion process. You've got power and speed. If you get outside of what's called the conduction zone, then you can end up with getting porosity from overmelting, porosity from undermelting. You can get too much surface tension in the melt pool and cause balling and other things like that can happen. that can be predicted and optimized through simulation. As mentioned, a lot of times there'll be parts that do not conform to your design requirements, and so you need to adjust for that. Different jobs being aborted through recoder interference or other problems that you have, you can often identify those problems before they ever happen. And obviously, as we mentioned, residual stress and even some of the post-processing challenges, we can start to alleviate some of those through utilizing simulation. So just a couple of quick examples here. Looking at build failure prediction, that's one of the easy ways that's very obvious, the value of being able to eliminate build failures. That's obviously going to save a lot of money. That picture in the bottom center, a bin full of broken and scrap parts. We want to avoid that. So, there are times where you're going to get that delamination. You can look at, for instance, on this turbine blade, if you want to try and print that blade with no supports, you can go in and you can predict and say, okay, well, if I do, I'm going to risk getting recoder interference out on those tips. So then you need to solve that problem either through design or through your build setup, orientation, supports, other things like that you may do. When we go into getting recoder interference, you can have recoder jamming, which is very expensive. You end up getting your parts ruined, your materials wasted. Oftentimes you need to replace your recoder, recalibrate your recoder mechanism. Sometimes you can even get a damaged recoder, which can actually sometimes be even more detrimental because you may continue the entire rest of the build with a damaged recoder, particularly if you have like a silicon spreader blade. And again, this is focused a lot on that laser powder bed fusion process. But if you take a chunk out of your blade, you're going to have thicker powder layer in those areas, and it's going to give you inconsistent material properties, deformation, visual problems. You may even have FOD deposited into your part. So simulation can help to predict when that's going to happen and help you avoid it before you ever have to waste any material or machine time. Another example, again, kind of looking at this build setup type of process. This is going back to that heat exchanger that I was showing earlier, but the part is designed with the original intent of hopefully not needing supports on that underside. But as you run a simulation, you can see that there is a fairly significant potential on that for this particular geometry to run into some recoder interference. You can solve it with support, as shown in the center. When it's supported, then you eliminate that potential for recoder interference. But one of the key things that I really like about simulation is that it allows you to go even deeper than just finding one solution to a problem. You can start to really explore what's going to happen and with different solutions for solving that problem. So for instance, on the right, instead of adding supports to be able to change the geometry there and being able to, which would lead to more post-processing, you can just quickly look at it and see that there are some small little areas that are stemming from where that blade crash, the recoder interference may occur. You can make simple design changes. And then in design, with very little material change, you can actually resolve the problem without needing that additional post-processing for removing supports. So again, just some value that comes through simulation where you can make some of those design decisions early on where you're able to save the greatest amount of cost later on. We all know that the earlier you make correct decisions, the more value those correct decisions bring. So as we look at a few of the things relative to the impact of simulation on additive manufacturing, these are just kind of some examples. This is actually based off of a satellite antenna component consolidation, but you can start to see things like cost reduction through utilizing additive for up to 75% by utilizing simulation and additive. So 75% in cost reduction, 80% in lead time reduction, sometimes that's even more important than the cost reduction. And when we look at efficiency, fuel savings, sustainability, being able to reduce the weight of the component by 95% is huge, and that's extremely important. So there's some really significant value of leveraging simulation and additive manufacturing together. So, just quickly as we're looking here, we've got the Ansys Additive Solutions. We really have a desire to get things first time right. We want to avoid build failures. By utilizing the gold standard of simulation, the Ansys solvers, leveraging best-in-class material properties and the powerful analytics that we have to establish the process property relationships. And this is all combined into an end-to-end solution. And when I talk about end-to-end solution with Ansys, I'm not really referring to just the process of receiving a part that has been designed for additive or not designed for additive, and choosing an orientation, supports, processing, looking at process simulation, going through that process. That is part of a workflow that we can do that's end-to-end. But one of the values that comes of simulation as a whole ecosystem is there are many, many more simulation capabilities outside of additive that can be leveraged. So, it goes across industries, solutions, applications, different simulation platforms. You can look at systems. You really get into a lot of these things when you get into software and system simulation, digital twins, and you can leverage that with physics-based simulation, multiphysics. If the part that you're designing, the system that you need to develop for your product is, it may have structures in it. You may need to look at fluids, electronics, semiconductors, optical photonics. You may need to look at 3D design, topology optimization. All of those things can be tied together in that end-to-end system, tied together with not only the design and engineering simulation, but also leveraging the manufacturing simulation. So now as we step into kind of question number 3, how can simulation technology really reduce your cost for additive? And we've, of course, touched on this a little bit already. But as we look here, this is just a quick example. We'll actually see this video a little bit later on as well. But in the powder bed fusion process, some of the problems that end up occurring as you're going through this process are manufacturing lead time, post-processing steps, manufacturing defects, certifications, plenty of other economic factors. And I think most of us have seen this curve before, most likely. And different processes, different industries, different applications, and even different materials are at different stages along this curve here. But one of the things that we're really trying to do is be able to eliminate a lot of these limiting factors, or at least find ways to get around these limiting factors to really help us get through that trough of disillusionment, moving up and to the right with the maturity of additive manufacturing technology, and helping the expectations to grow, but grow in line and in accordance with the maturity of the product, so we can rapidly move up and to the right and realize those life-improving benefits that we talked about earlier. So I think a lot of people know Tim Gornet. When he was the RPC operations manager at the University of Louisville, he was utilizing the Ansys additive tools a lot, made a statement that I really, really like. Ansys Additive Suite has cut their print builds from 4 to 5 builds to 1. You can see already that, that's huge savings when you're trying to print parts. If you can start to get them right most of the time on your first try, said that they were there at 90% first time build success. And so for anybody who's been working with laser powder bed fusion, what an achievement that really is. Another example, Mechanical racing systems. This is just kind of quickly looking at another example here. We won't go too much in depth on this. If you're interested in learning more about PANCL and some of their use of simulation, there are other webinars. In fact, there's one tomorrow. But some of the key challenges of this particular application here was looking at deformed parts after printing. You're getting that recoder interference, time and cost to qualifying a machine, and really the value proposition for leveraging simulation is to get that automatic distortion compensation, make sure that your part deforms into shape instead of out of shape, qualifying your new machines faster through multiple mechanisms, both the reliability of being able to print your parts, not wasting time on failed builds, as well as being able to optimize the process parameters, and post-printing validation analysis. So being able to take that analysis after you've printed and run it through validation simulation to make sure the part in the as-built state will perform as desired and as designed. So just another quick statement here. From PANCL, in nearly each step of the design and production process, Ansys products are utilized to achieve the best possible results and meet the high standards of our customers. And PANCL Racing really does have high standards from their customers. The racing industry really needs very, very high performance parts. So as we look at kind of doing a little bit more on summarizing some of the ways that simulation can help, you're able to improve in multiple areas, like improving the design cycle, insight into AM processes, machine productivity, material usage, repeatability, quality. You can start to reduce things like build failures, non-conforming parts, your post-processing, reduce the empirical testing, equipment maintenance, environmental footprint, lead time, development time, all these things that can be reduced. And you can also dive into being able to more effectively develop new materials, new machines, new parameters, developing custom microstructures, and developing the desired mechanical properties that you want for your specific application. So one kind of last little example before we jump into a little few slide case study is just when we look at being able to utilize simulation. Here's an example out of University of Louisville. When you're going through the process, a lot of times you'll come up with a concept, you'll come up with a design, and then it's a pretty iterative process as you go through validating that design before you're ready to go into actual full rate production, fabrication of those parts. And a lot of times those iterations are driven by, in this particular example, you can see there was support delamination. There is deformation in the parts. You may need to print sacrificial support structures, different things along those lines. But a lot of times you don't know exactly what you're going to need when you are actually printing a part. And if you've started to print this and you get, say, 1/3 of the way into the build and the support structure delaminates, well, at that point, you know that your support structure is not sufficient. So maybe you go in and you change your support structure and you go ahead and you build your part. Maybe this time you get 2/3 of the way into the part before you find out that there's going to be recoder interference because it's deforming too much. So you go through and you change something in your design to be able to make so that you don't run into recoder interference. This time, maybe on the 3rd try, maybe you get all the way through printing the entire part. You just spent 70 hours printing a part on a laser powder bed fusion machine. And as you get to that point, you realize that the deformation in the part, maybe because of adding in some sacrificial support structures, cause so much deformation that the part is no longer usable. And so you can really see how going through these iterations, yes, you can solve problems oftentimes one by one, whereas with simulation, you can look at it holistically. You can look and you see how much residual stress you're going to build up in those supports. You can see where you're going to see recoder interference, and you can start to see the deformation in the part. And so you can address those before you need to make multiple iterations. And so it significantly reduces that validation time frame and gets you to fabrication faster. So now just jumping into another case study, simple bracket, it's a nice topology optimized part. This was in a partnership with ProM, just trying to help them to be able to build this vehicle. And as we look at this, those two areas that are marked in gold boxes on the right are their areas of main concern. Those are the interfaces, and they really need to make sure that those locations conform to the original design intent. So the idea here was that there's a preliminary analysis of the nominal geometry, run that through and obtain the compensated geometry by using simulation. And then in this particular case, they printed both the nominal geometry, the original geometry, as well as the compensated geometry, and measure them. And so, as we go through this process, you can see the predictions relative to the simulation results. You can see how they match very well, where you're going to see that deformation. And then the really valuable part of this is that the idea here is, you want to be able to build a deformed geometry without having to rebuild the part. And so the original deformation without the compensated geometry was 2.2 millimeters. In fact, that was too much to meet their tolerance ranges. However, with the compensated deformation, that was driven down to just plus or minus 0.23 millimeters. And the maximum axis misalignment, which is extremely critical in this particular application, was less than 0.5 degree. So a very successful example of distortion compensation. So as we look at a few of these different examples, we can really see how simulation can drive the reliability of additive as well as reducing cost. So now I want to jump into some things maybe slightly more technical here as we're going into a little bit of detail about some of the terminology relative to additive simulation. There is a lot of stuff that we could go into. I'm not going to go into too much, and I'm not going to go too deep, but just to kind of bring a little bit to bear here. Again, same video as before. The reason that it's here is because as you're looking at this, and you can see, like this is one of those examples where it's printing supports. There's a part. Every other layer it prints supports, and you can see some of that stuff happening in this part. But you can see as the laser hits that powder, you're going from somewhat elevated temperature material to a temperature that will cause the metal to melt almost instantaneously where that laser's hitting. And if you look at these images on the right, as the laser hits the material, it's going to heat up, that's going to expand. You're going to see some expansion there. And then as it cools, you're going to see consolidation. It's going to shrink. Not only do you have just the material heating and cooling, but you also have the consolidation of powder into solid material. And so that's really that shrinkage in the material creates that residual strain, which leads to the residual stress. That is what leads to a lot of the problems in multiple different additive manufacturing processes. When we look at DED, when we look at powder bed fusion, with the binder jet sintering process, as you put it in the oven, it really is just that consolidation of material and that cooling, that consolidation cooling, but you're still introducing that residual stress and strain into your part that can lead to things like that picture on the bottom right, where your part it can rip itself apart. You can pull the part from supports, you can pull supports off of the base plate, but it leads to a lot of problems. And so that residual strain that's happening through the thermal shrinkage in the process is a key contributing factor to the reason why simulation is so valuable in additive. So one of the things that we're going to talk about moving forward now is going to be a few different methods for different skill levels of simulating. So what we're looking at right here now is just kind of a fun video looking at discrete element modeling. So, you can have gummy bears, potato chips, fibers, foils, all sorts of different things. But discrete element method modeling means that you're taking each of those individual elements and you're modeling them. So when it comes to particularly like laser powder bed fusion again, looking at the metal process here, we've got some different laws that that we can put into play. You know, Newton's laws are always there, gravity is always there, and you can start to apply some of those laws to individual powder particles. So this is something that is available within Ansys to be able to go through and do discrete element modeling. So, you know, you can see kind of this example here is if you've got a recoating, you've got some powder there, you can start to look at what's going to happen with the with the particle dynamics as you go through this process, and you can see how recoating is going to happen, how the materials will move, what that deposition is going to be like. You can start to really capture some detailed information. This is one level of mesoscale modeling, and we're going to talk through a few different types of mesoscale modeling and getting into macroscale and how does this work. But when we're talking about mesoscale, you know, we're really trying to get into some of that intricate detail of the process itself. So as we move through just having a discrete element model, then you can move into looking at how that relates to thermo-fluid particle dynamics. So you can apply an energy source to those elements and see what the melting and cooling is going to be. So additional mesoscale modeling is getting into a scan pattern-based thermo-mechanical modeling method. And so in this particular method, you're not necessarily taking into consideration the individual powder particles. You're more considering the powder as a continuum. And so that means everything's connected together. But then at the mesoscale, you're taking into consideration the individual scan vectors of a part. And what we're looking at here is specifically with laser powder bed fusion, where you can take in to consideration individual build files from specific machines, generic build files. With the DED process, you can also follow the G code and trace out how the thermomechanical solution is, just go through that thermomechanical solution based on what's going to happen in your specific part build. And so then kind of jumping to macroscale, you get into the macroscale modeling lump layer. I'll go into each of these with just a little bit more detail. We've touched on them a fair amount here, but you get into lump layer, which is really, just being able to take some of these mesoscale results and lump them together into an efficient macroscale model that can help you really drive the fidelity of your simulation. So, as we go back to that mesoscale thermo-fluid modeling, you can start to look at things like, what is the influence of your scan trajectory, the number of lasers, the laser power, beam diameter, multiple materials, the gas in your chamber, what's the powder bed density, deposition thickness, base plate temperature, materials. You've got all these things that you can go in and look at. And I guess just kind of, as a statement, this isn't the way that we usually don't take this level of detail into the macro scale, just because in most cases, it's not fully required in order to get a really valuable result. Some of the other mesoscale scan pattern-based results are quite valuable. But as you get in here, you can start to look at things, the capabilities there. If you look at that upper video, the laser is moving at 7 meters per second, so 7,000 millimeters per second there, and there's not enough heat transfer to fully melt all the material. But if you go to 1,500 millimeters per second, then there's plenty of time to be able to get a viable melt pool width and depth and full melt there to try and avoid getting porosity. So those are the kind of things that you can look at with this thermo-fluid modeling. As we kind of jump to what I was mentioning before, the mesoscale, you can represent the laser with a Gaussian heat flux model. So you'll being able to look at that. Depending on the process that you're looking at, as mentioned, like for instance in DED, that G code drives the element activation. with powder bed fusion, we'll often drive it. We'll do a full scan pattern, and we have several different layers or levels of fidelity that you can use in the mesoscale. When we look at this, we can just put anisotropy based on all of the individual scan vectors in a given layer, or we can go through and apply the full heat flux, the laser model, to those scan vectors, and that's what we call the thermal strain. We actually have introduced a machine learning thermal strain, so you can get that that highest level of fidelity in much less time. So that's kind of something that's there. You can take all of those different levels of mesoscale and apply them with temperature-dependent material properties to be able to get a good thermo-mechanical simulation. One example of where that mesoscale applied to the macroscale, so getting into still running that lumped layer, but after the mesoscale simulation can make a difference. This is an example where Additive Industries, this is a part that they build quite frequently. A lot of people have seen it before. It's this nice little heat exchanger, but you can see the shrink line. Almost all the time, if you've built parts in powder bed fusion before, you know that that shrink line is going to occur. When we use the inherent strain model, we are able to predict that that shrink line is going to be there, which is really good. But if we use that mesoscale analysis, the scan pattern analysis, then we can actually pick up with higher fidelity the transition and the gradient of that shrink line and the actual magnitude of it, so that you can more effectively solve that problem. So just an example of how mesoscale modeling integrated with the macroscale modeling is really valuable. I'm going to move fairly quickly here. This is in almost all additive process simulation, you're going to be looking at some level of macroscale because it's very efficient. And the idea here is that you take multiple powder layers, your physical layers, and put them into a certain element size. When you're running the process simulation, you're going to consolidate a lot of that information into an element thickness, which is usually larger than the actual powder layer thickness. And so this is that next level up analysis. With Ansys, you can do that mesoscale and apply it to the macroscale. But the strain as you heat and cool your parts is really driven. There's multiple different components to that strain. You've got elastic, plastic, thermal, phase change, and creep strain. Usually that's determined, or you usually drive that through some sort of calibration utilizing inherent strain. And so you're going to end up with multiple different layers that you're going to be applying the strain to. And as we look at this, so again, just kind of looking over here, you got layer one, you're going to have some equivalent total strain for layer one, which is probably going to be different than the equivalent total strain of layer two, so it shrinks differently. Layer three, yet again, a different amount of total strain, which is what leads to the deformation in the process. And so as you go through the process of being able to take that lumped layer approach, it's very efficient, and you can go through and model what is happening with your geometry as you take all of those distinct levels of strain and apply them together and see how it's going to impact your part. So some of the things that you can get out of this are things like thermal gradients. You can look at the powder impact on the thermals. What are you going to get for temperatures? You can get residual strain, stresses, distortion on and off plate before and after heat treatment. You can have multiple parts on the plate. You can look at hot spots, recoater blade, and as I've talked about several times, that distortion compensation is really valuable. So what tools should I use? And this is kind of a hard question to answer because there are quite a few different tools, and there are a lot of different applications and processes and different things that you need to direct at. And so first and most obvious answer to that question is, if you're doing laser powder bed fusion, use our powder bed fusion module. If you're doing directed energy deposition, go to the DED module. If you're doing binder jet sintering, go to the metal sintering module. we have these tools out there and available, so you can go and try and solve all of these different process problems. So when we're looking at this, though, it really, which tool to use really depends on what you're trying to find. If you're trying to see how one part impacts another one, then you need to use the tool that allows you to have a build plate, a full build, where you can look at the impact of those different parts on each other. If your main concern is the temperature, and that's that part of your part, what's your microstructure going to be? What is the heat affected zone from the lasers, things like that? You go into a temperature solution. If you're trying to look at displacement, strains, and stresses, then it's also going to depend on what type of geometry. Inherent strain is going to be actually pretty good for a lot of bulky parts. In many cases, when you get into thin geometries, you really need those mesoscale adaptations, the scan pattern influence. And as you're going in there as well, when you get into especially thin-walled, multi-wall geometries, being able to utilize like the Ansys Mechanical solution there, where we have what's called the layered tet mesh. It's a tetrahedral mesh that can conform to your part geometry a lot better than a uniform hexahedral or a voxel mesh can. And so, it kind of depends on the type of geometry and different things that you're doing. But again, thin-walled features, things like that, mesoscale and layered tet are extremely valuable. Bulky and maybe where you don't need a significant amount of fidelity, just a standard isotropic inherent strain is going to be totally fine. When you're looking at build defects, and you're looking at crash severity, different things like that, then if that's what your main concern is, then you'll utilize tools where you want to look at that. We have the ability to add heat treatment to these different processes. And if you're really trying to understand the details of what's happening in the part, and you want to know what the powder influence is on your parts, you're really trying to figure out that thermal and get into a fine detailed analysis, you can put in the powder into your simulation as well. And so there's a lot of capability there to be able to see these different things. One really nice thing with utilizing Ansys for simulation is that Ansys has a lot of capability beyond just additive, as I had mentioned before. So, you've got your material properties. You can go, this is just a quick example of looking at like putting it into Ansys Motion. You've got vehicle dynamics. You want to understand the fatigue life of a component. And so you've got your, you can take your load history, map to unit stress load cases, including the manufacturing history, and really help to drive fatigue life to where you want it. I'm going to run through this pretty quickly, but this is just one example of a femoral implant, a femoral stem. And so, you've got your basic geometry, the gates, so the loading when this is implanted into different humans, different conditions, different strides and things like that. You can have information like material cost and printing process parameters, manufacturing parameters, dump all of that into Ansys Model Center. You can tie that together then with the structural analysis, your lattice optimization, your process simulation, and really come up with an optimized design that will give you exactly what you need for that. And it can give you different options depending on the different types of gates and different scenarios that you may need to look at. Powder bed fusion, when you're looking at process parameter optimization, again, you're going to have power and speed. You want to figure out that right combination to be able to optimize your process parameters. So within that area called the conduction zone, meaning areas where you're going to get a good full melt on your materials, generally, if you can move down and to the right within the conduction zone, you're going to be building as fast as possible with as little power as possible, so efficient. And so, you can utilize simulation. You've got a lot of potential to put in these different parameters. This is leveraging a tool called Ansys Additive Science. And by utilizing this, you can actually start to drive process parameters that will help you to avoid keyholes, avoid balling, avoid lack of fusion, while being more efficient. And so that's also an extremely valuable tool when you're trying to really optimize your production. And then kind of as a final thing here, as we're looking at some of those tools, you really need something to manage your data. As you go through the additive manufacturing process, you've got machine, material, application, different batches of material. You've got all of this information there that needs to be controlled and contained and tracked, especially if you're going into production and qualified production. And the Ansys Granta MI database allows you to take all of this data from preparation, material, design, process, simulation, test, measurement, and keep it organized. It is so much more efficient to truly have all of your data organized and tied together for the qualification process. And it truly can help to significantly increase the speed of being able to get qualified materials, parts, and equipment. So I'm just going to hit this very, very quickly because it's just some of our most recent highlights. Automatic distortion compensation, and I probably actually should put on there optimization. We created a loop. So when you create a distortion compensated file, and if you were to just directly print that, your input now is a little different than it was before. And so you would expect to actually get some difference in the output. And traditionally, anytime you have a distortion compensated file, if you want to verify that, you'd have to go back through and set up and run a simulation. We've created an optimization loop where you can identify your max deformation, your max average deformation, and the max number of iterations that you want that simulation to run through the loop. And it will, you can set it and forget it type of analysis where it will just automatically run through the cycle and give you an optimized distortion compensation factor and geometry that has already been simulated to make sure that that distortion compensated geometry is going to fit your requirements. We've released binder jet printing, put more and more capability into the Ansys Mechanical application for additive. And so now you have a lot of that mesoscale capability with scan patterns and as well as machine learning, which has been a huge improvement on the overall speed for doing that machine learning, for a thermal strain analysis at the mesoscale level. So we all know that in additive, there are needs in methods, materials, technology, workflows, machines. That's really the ecosystem that we're focusing on trying to provide solutions through. So we're working with machine manufacturers, we're working with material manufacturers, we're integrating with software to try and provide the best experience for users to provide those insights that I mentioned earlier that you need where and how you need them in order to be able to truly develop those life improving products that additive manufacturing can bring. In conclusion, there's a lot of words here. The things that we talked about, additive can make a difference in the world. Simulation can truly help by reducing costs, improving reliability, and shortening the qualification cycle. We talked about some applications where additive is good. We talked about some problems that can be solved through simulation and why it makes sense there. We talked about how you can actually save money by utilizing simulation in your additive manufacturing process. We talked about several of these different terms that are used in simulation for additive. And then we talked about some of the tools that are out there that you can use to solve those additive manufacturing problems. And with that, I will wrap up now and turn it back over to Jason for some question and answer time.
All right, great. Thank you, Chris. That was a great presentation. Very, very informational. So yeah, we'll now head into the Q&A session. If you have not done so already and you do have a question for Chris, please enter it into the Q&A space. Let's see. So one question was when you showed the gummy bears and the different strands falling, was that just for fun, or is that representative of different shapes of molecules, or can you pick different shapes, sizes, and things like that?
Yeah, I guess that The video itself is just trying to demonstrate the ability of a discrete element method solver to be able to take multiple different types of geometries and discretely model each of them individually. So, you know, for instance, with normally with powder bed fusion, for instance, or even flow in DED, you're almost always just going to do spherical geometries and run with that as a close approximation.
Okay, thanks. I think that's where the, yeah. Okay, thank you. Let's see. Got another question here. Sorry, I joined late. Is there any way to get the presentation file? So we will share. I was going to touch on that at the end of the presentation, but thanks for asking. These are all uploaded to the America Makes YouTube site. So you can either just go right to the America Makes YouTube page, or you can go to our website, americamakes.us, and we have a events page there where you can find links to these webinars as well. All right, Chris, you must have done a great job. I don't see any other questions coming in. So let's see, I'll go ahead and wrap up the presentation or the TRX webinar for today. Chris, thanks again. That was a great presentation. If you do have further questions for Chris, you can reach out to him directly at the email on the screen. And then just another reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to me, Jason Thomas, at jason.thomas@ncdmm.org. So Chris, thanks again. Everyone else, have a great day.
Thanks, Jason. Thanks, everybody.